So today I'm going to talk to you about this path of mine in chemical informatics. Um, this was not by design by any stretch of the imagination. When I became a chemist in 2000, the thought was that I was actually going to go to MD PhD program. And so I had a family and I realized pretty quickly that that wasn't going to get me what I wanted in terms of my personal life and the interplay with my professional life. So I decided to go on another path. I got a second master's degree in pharmacology from Georgetown University, and then decided that I wanted to work in pharma. I did that for a little while. It was an unmitigated disaster for a multitude of reasons, not the least of which is that I didn't have a PhD. And so, most scientists in, organizations like pharmaceutical organizations have PhDs. And while I did have a dual master's and a lot of experience and had published, it just didn't quite get me the opportunity that I felt like my talent deserved. So I started thinking about ways I could leverage my chemistry background into another field. I had done, research for my master's in chemistry. I actually looked at a lot of protein sequencing databases. And so that's when I first started getting into what was then thought of as bioinformatics. And so I leveraged bioinformatics into analytics and then into data science. And now I'm back to informatics, which is, as CJ mentioned, what I'm completing my PhD in. I got into chemical informatics technically last year. So I initially got into informatics, worked at a lot of different organizations, startups, was a consultant with the government, and made a decision primarily based on work environment. My first job as a chemist was at this organization, a DC organization that works with the FDA in the drug approval process. And so I came back to this organization because, quite frankly, it had been one of the best work environments I had ever been in. And as a Black woman in a field that doesn't have a lot of representation, a positive work environment was exactly what I needed at this point in my career. So I came back to chemical informatics. And so one of the projects that I'm working on at work, we are looking to characterize potential mutagenic impurities. And so that kind of took me down a path of how do I apply machine learning? How do I apply techniques in chemical informatics to get to the goal of classifying compounds? So back to the screen sharing. And just an FYI, this is probably going to go a little longer than I thought. I wanted to make sure I covered everything. I'm really excited about this topic, and I hope you all enjoy it. Okay, pick this right screen. We're going to share. I'm also going to do a little bit of, I don't know if it'll be live coding because things can go wrong when you try to live code. So I'm prepared to live code. If it doesn't work, I have the backup code that has everything already worked out. Okay, here we go. All righty. Okay, so I am actually a chemical and health informaticist. And the reason why I keep the health informaticist title is because a lot of the work that I did initially in informatics was in the healthcare space. And I actually still continue that work as I'm completing my dissertation project, where I'm looking to use machine learning to make predictions about the health outcomes of Black women living with HIV. All right, so a little background on the history of chemical informatics. It's defined as an interdisciplinary field, and it focuses on the collection, storage, analysis, manipulation of chemical data. It actually arose around the 1990s, although there's some argument about the fact that it arose decades earlier, and it represents the fields of chemistry, computer and information science, and drug discovery. Drug discovery is actually where chemical informatics was initially used a lot, because obviously it helps to expedite the process of creating drugs, and then from there we can go to clinical trials, and then we can use them in the population. But chemical informatics also has roles in fields like biochemistry and genomics. So as I mentioned, chemical informatics is really an interplay of a lot of different fields. But it's also related to some other fields that you may have heard of, including computational chemistry, molecular modeling, and computer-aided drug discovery. So when we talk about chemical information, we have to talk about ways that we can store that information, and more importantly, ways that we can store it where it'll be accessible on a computer. So there are three main forms of structures, forms of chemical ways to store chemical information. I'll get this out. The one that I have a preference for is called an Inchi key. So Inchi key is made by the IUPAC, this international foundation, which creates what's called systematic or IUPAC names for chemical substances. So that might be something like 2-diethyl methyltriene or something like that. So that would be what you would call an IUPAC name. So an Inchi key, which again, it was created from the IUPAC organization, is a chemical identifier that's made of ASCII characters and a fixed 27 character length. That's really, really important. And I'm going to show you examples of this in some subsequent slides. So what I like about Inchi keys is that it's a unique 27 length character, and you can easily search the web for it. So in other words, if I have an Inchi key of a substance, I can just put it on the internet, Google it, and I'll more than likely get referred back to the chemical substance that it represents. The other linear method for representing chemical substances are called SMILES. So it's Simplified Molecular Input Line Entry System. So this is a text format that was created to describe the connectivity and the chirality of chemical structures. So there are two forms of SMILES. There are canonical SMILES, which describe chirality and connectivity. So this, we're going way back to Orgo, nightmares of organic chemistry, y'all. So really important in chemical informatics. And then also the isomeric SMILES, which specifies isotopism, which is essentially the charge on a molecule. It also describes chirality and the configuration about double bonds. So I mentioned Inchi. So there's an Inchi notification or designation. There's also Inchi key. So Inchi describes chemical layers, chemical structures and layers. It describes chemical formula, bond connectivity, and stereochemistry. The reason I don't prefer those is because it's a real complicated mix of characters and strings. I mean, characters and alphanumeric alphabet and numbers that make it really hard to do a simple Google search for. So that's why I prefer an Inchi key. Also, when you're using, a string that has special characters, it can make it difficult to process if you want to import into Python, things like that. So that's why I prefer the Inchi key. So this is an example of what I was saying about the complication of Inchi key versus Inchi. So this is some chemical information on ethanol. You have the molecular formula, IUPAC name, isomeric SMILES designation, which typically, isomeric SMILES are typically the main bonds that are in a particular chemical substance. You have Inchi key, so as I described, it's a very unique 27 character string, and then you have Inchi. So can you imagine trying to import this string into Google and what you might come back with as a hit, as opposed to the Inchi key, which will give you 9 times out of 10 the exact substance that we're trying to look up, and in this case it is ethanol. So most of your chemical databases are going to give you this basic information. So I just wanted to share that on the screen. Okay, so now we need to talk about how do we store this chemical information, different types of file types that you commonly find in chemical informatics. So some of these probably look familiar to you. And I'm not sure if Sia is on, but Sia was the one that actually helped me get started using XML files, because up until I became a chemical informaticist, I never really did a whole lot with XML files. Most of what I dealt with, quite frankly, were CSV files. So working as a health data analyst in a hospital, if any of you attended the previous lecture, there was a lot of talk about Excel spreadsheets, Excel files in the form of CSV. Are very common and popular in healthcare organizations. But coming to chemical informatics, now I'm dealing with these humongous files, and obviously something like XML and JSON allows you to store chemical information and store all this data without taking up a lot of storage and memory. So XML was what Sia helped me with a couple months ago. It's a text-based format that's used to represent chemical information. There's also a specialized form of XML called CML, Chemical Markup Language. I haven't really had a lot of experience with CML. I personally try to deal mostly with JSON. A lot of the databases that I deal with allow me to export data in JSON. So that's probably the form that I use the most. So JSONs are chemical identifiers that are made of ASCII characters. And it's also a fixed 20, okay, this is not the correct information here. I'm not sure how this got in this slide, but that information refers to Inchi key. So ignore that top line, and when I make my slides available, I'll be sure to delete it. So my apologies there. Excuse me. But you can search, do web searches for JSON files. And more importantly, they're readable by numerous programming languages. Python, R, Java, C++, and actually even Excel can process JSON files. Finally, we have mole files. So a mole file is a representation of a chemical substance, whereas a structured data file contains either a large mole file or it contains multiple different mole files. It provides information about the number of bonds, atoms, and how they're connected to each other. The SDF file stores structural information associated with the data. So in addition to the information you find in a mole file, you'll also find additional information in SDF files. Okay, so what does that look like? Hopefully this is showing up pretty good. So what I have on the left, I use VS Code as my programming editor. I can run Jupyter Notebook, I can run R, I can do a lot of things with this. So I love VS Code, and then I can customize it and get these great colors as well. So what I have on the left is what's called an XML file, and this is the XML file that represents, it should represent the compound ethanol. What I have on the right is a JSON file, and this is a JSON file that I got from PubChem. And again, you can go to PubChem, you can actually export as a JSON file, and this is what you will end up with, and it contains a lot of different chemical information. So this is a difference. These are the two main types of files that you find for chemical information. Again, I deal mostly with JSON files, but XML files are quite usable as well. Okay, so here are examples of the mole and SDF files. So what you see on the left is the mole file for ethanol. So the number designations represent the number of bonds, the number of atoms. The 3 is the number of bonds, the 2 is the number of different atoms. Here you see the carbon, and then the oxygen. And then they do these calculations to determine distance to each other, bond angles, and things like that. There's a lot more information that'll be provided in the slide if you want to get more detailed information about what the mole files are. A lot of what I do as a chemical informaticist is I'm going back and forth between different versions of chemical information. Sometimes it's easier for me to work with a mole file. Let's say if I get it from a stakeholder, it's a mole file, or if they send me a JSON. So I'll show you in some further slides how I can interplay with different types of files. It's really kind of cool. So on the left, remember, I'm sorry, on the right, remember I told you that an SDF file contains not just the mole file information, but it also contains other additional information about that compound. So in this particular SDF file that I got from Chem BI, which is another very popular chemical database, I have the IUPAC name, I have the molecular formula, molecular weight, I have the charge, SMILES, a string, I have the INCHI key, INCHI, etc. So again, the difference between the mole file and the SDF file is that an SDF file typically is much more comprehensive in the terms of the chemical information that'll be present there. Okay, chemical databases. So there's a lot of different publicly available chemical sources of data. These are probably the ones I use the most: PubChem, Chem BI, ChemSpider, ChemMBL, CAS, which gives CAS numbers, which you may be familiar with, a type of numerical identifier for chemical compounds, and then finally ChemID+. So these are just my personal favorites. There are a lot more out there. I mostly try to use the ones that you know, are curated in the United States, and PubChem will be at the top of that list. Okay. All right, so this is an example of what you would see if you went to PubChem and looked up the substance ethanol. PubChem has their own, what they call chemical identifier. The number here is 702. This probably isn't you know, synchronous with other databases. They typically do have their own identifiers for chemical compounds, but there are a lot of things that they do have in common. For example, the IUPAC name will be consistent. IUPAC is a standardized name for a chemical substance. They're giving information about the isomeric SMILES, INCHI key, INCHI, and then there's also some information about when this entry was put into the database. So 2004, this is not a very old database, as you can see. You'll also see with ethanol, this object over to the left is the chemical structure of ethanol. You can actually look at different views of it. There will be a 3D view that you can look at. There's this ball and stick view that you can look at. And then here you'll see different names of ethanol, or different substances that contain ethanol that are listed here. So that's just an example of what you see when you go to PubChem. Chem MBI is another database that I mentioned. This one, as you can see, a little different than PubChem. They actually show you more of a 3D representation, or actually a 2D representation, but it gives you more information about the, the atoms that are connected to make ethanol. It has its own identifier. Remember I mentioned before, the different databases have their own way of, identifying chemical compounds. Now, what's really cool about Chem MBI is this mole file. This is actually the mole file you just saw. That's where I got it from. So this database allows you to download ethanol and everything about it as either a mole file, XML, or SDF file. So this is actually where I got the information you just saw on ethanol from Chem MBI. Okay, so I'm going to stop right now. Does anyone want to ask any basic questions before I get to the nitty-gritty of the presentation? Feel free to put, I can't see the questions, CJ, so if you could read them, that would be great. Assuming there are any. Okay,
no questions in the chat yet.
Okay, fantastic. So we're going to keep it moving. I'm sure there might be some after I do this part. So software and programming languages used in Chem Informatics. Before I get to that, Chemdraw is a, wow. So I actually used Chemdraw back in 1985 because I was taking organic chemistry in 1985. So I just gave my age away, but it's cool. It has changed a lot from when I first used it. This is not what it looked like by any stretch of the imagination. So you can imagine like the game Pong, right? What it looked like back then, like when I was playing it, and the way you guys have these 3D, you can do virtual reality and all that. So it's something very similar to that. But at any rate, it was developed by a gentleman by the name of David Evans. It's now owned by Perkin-Elmer. And for any of you that are interested in chemical informatics, I would strongly urge you to get an account at Perkin-Elmer. They have a lot of videos on chemical informatics. Really helpful website. I haven't even had a chance to delve into everything they have because, again, I've only really been a chemical informaticist for about a year. My anniversary is on the 9th of November. But at any rate, check the site out if you're really interested. So there are a number of different file formats that you can use for Chemdraw. When you create files in Chemdraw, you will end up with a file format called CDX, but they also have something called CDXML, which is supposed to mimic XML. I actually haven't tried it yet, so I don't really know. But more importantly, I can export in any number of different formats, including the mole format and the SDF format. And the reason that's important is because those mole formats can actually be used to either import directly into a programming language like Python, or I could use that mole format, put it into a search engine in PubChem, and come back with the substance of that particular mole file represents. And then I actually have a video of how to use Chemdraw. Really helpful. So this is what the interface for Chemdraw looks like. Over here you have like different, like a lasso. You can add different types of bonds. You can do chemical reactions. All your different 6-membered ring, 5-membered ring, 3-membered ring. These substances here are because they have a biological package that goes with Chemdraw as well. I forget what I think it's called BioDraw. I'm not real sure. But anyway, so in this particular example, what I'm showing here is that I put the name ethanol in, and then I went to structure and I said, convert the name to a structure, and this is what it gave me back, right? So that's exactly the structure of ethanol, written in what I would call a ball and stick format. Okay, so how is machine learning used in chemical informatics? So machine learning, as a lot of you may know, are basically ways to classify things. So in this particular, as it applies to chemical informatics, we're looking to classify chemical compounds. That's one use of it. So remember, I talked about how I'm doing some work with potential mutagenic impurities, and the reason those are important is because obviously when you take Tylenol, you don't really want to be taking any of the oh gosh, I've lost the thought of what it is. In a chemical reaction, you have these byproducts that are produced. Sometimes they're really super harmful and sometimes they're not. So those byproducts can sometimes be in a classification called potential mutagenic impurities. And so a lot of the work that I'm trying to do is to look at when a chemical reaction occurs in the production of a drug, these impurities that are produced, how toxic are they? What are the human limits for those molecules? But before we can determine all that, we have to characterize them. And so that's where machine learning comes in. So this is a very particular type of method that's called the Tanimoto coefficient. Now, if you look at any of the machine learning techniques for classifying chemical compounds, they're pretty much all going to start with this. The Tanimoto coefficient is also known as the Jaccard index, and basically it's used to evaluate the similarity, structural similarity of two compounds, with the idea being that two compounds that are structurally similar probably behave similarly. So I'm going to show you an example with some live coding in Python where I've looked at ethanol, and I'm going to compare it with a known potential mutagenic impurity called dimethylethylamine. And we're going to see how how structurally similar those two compounds are. Okay, so any value greater than 0.7 is considered structural similarity. Now, fingerprints are, and this is actually working backwards. So I'm starting with the Tanimoto coefficient. Well, what gets fed or evaluated in that Tanimoto coefficient are what's called fingerprints. And fingerprints are descriptive strings that are used for any number of purposes. But for what we're doing, we are going to be looking at the similarity between molecular structures. They're also used in predictive modeling. So a fingerprint is a molecular structure that is encoded in a format which is ultimately readable by the computer. And what happens is it takes that format, converts it to zeros and ones, which is how computers read information, and then it will create a structure based on those series of zeros and ones that were put together. And this is probably a little confusing now, but I'm going to show you in live coding exactly what it looks like. So what is this algorithm looking at when it's creating these fingerprints? Well, it's looking at three different things. It's looking at the atom itself. It's looking at the atoms that are next to that one. And then it's also looking at the bonds that are connected to it. And then it's coming up with what it calls a fingerprint. But fingerprints are actually originally what we call descriptors. A group of strings of descriptors are what equal fingerprints. Okay, so that's how the two words are related. So as I mentioned before, you have your set of descriptors, which actually are multiple fingerprint sets, and they are binary, zeros and ones, and it's converted into that using the software so that it can be converted to a form that actually gives a chemical structure, as well as being a format that can be readable by the computer. And so we call multiple strings of descriptors fingerprints. Again, it'll be a little more clear when I go through the code, which I actually am getting ready to do right now. Fantastic. Yeah, this is the exciting part. Okay, so I'm able to use a software package called RDKit, which has all of the chemical information from Chem MBL and run an analysis in Python. So now what I'm going to do is show you a little bit of what that looks like. So let me stop sharing my screen. I'm going to go over to VS Code. Oops, went a little too far. Let's see here. So I'm going to end the show. And now I'm going to share my screen and show you my VS Code where I'm actually, I've got the RDKit pulled up in my Jupyter Notebook, which I run in VS Code. One of the things you'll have to do when you want to use RDKit Python in Jupyter Notebook is, oh wow, it just came up. Okay, you will have to create an environment with which to run RDKit. So when I go to select to run my first two lines of code, it says I have to select the kernel for running RDKit. And as you can see, I uploaded RDKit using Conda. Again, I'll have all of the links to where you can do this step by step, just as I've done here. I'll provide that on the slides. Now, just a FYI, the slides will not be available until January, the slides in the video. However, you can feel free to Google, like do a screenshot of the final slide where I have my references, Google what I have on there, and then you can start working on that yourself until you can get a hold of the information I'm providing here. So I connect to my kernel, which is my programming environment for RDKit. And this is taking a minute, unfortunately. Live coding is so nerve-wracking, you have no idea. And hopefully this won't take too long. It'll take but a couple of seconds earlier.
Hi.
I'm gonna give this another minute, and then I'm gonna walk you through. That's why I had it already on here.
Hello.
Are you talking? Is that you, Sia?
Yeah, hi. I was gonna say there was a question way earlier from Christopher about
Yes.
how do you title yourself professionally having such a vast amount of great education and professional experience?
Okay, say that one more. The first part one more time.
Like, how do you give yourself a title? Like, what is your title with
What's
all
my
the
title? Yeah.
with the
So I kind of base my title on what I'm doing the most right now. So right now, where I'm mostly concentrated with my work experience is in chemical data. Um, Doing a lot of Python, some R, some SQL. We talked a little bit about that early in some earlier sessions. So that's where my title Chemical Informaticist comes from. But because of all of the work that I've done in the healthcare space and informatics, and the fact that my dissertation topic is in that area, that's why I'm comfortable using that title as well. The title that I don't really use much, even though I did have it at one point, is health data scientist, because first of all, I didn't really like being a health data scientist that much. I did a lot of data cleaning, and it's not really my thing, and a lot of data engineering, and that's definitely not my thing. So, and I'm not, working in that space that much anymore. Like for me, data scientist really, for what I did, was more like data engineering, and I'm definitely not a data engineer by any stretch of the imagination. So that's kind of how I determine that. But then I've also been a professor, and I work and I teach. And so I just kind of look at kind of what I do in my life the most. And that's how I kind of come up with the titles. And of course they have to match, my work, job descriptions and all that kind of thing. So that's how I do it. I think that actually brings up a good point that I very early, when I was trying to transition from the bench. So I'm a bench scientist, and I want to be, go into a data career. Um, One of the things I had to do really early was kind of decide what area did I want to focus in. And so it was easy for me to get my foot in the door to leverage what I already knew. So I did science. I had started to do, like, I had, taken an MCAT, and I had, been pre-med. And so I had all these healthcare courses as well. And then I also knew that I wanted to focus in health information technology. So I took some additional courses in that. And that's kind of how I framed what I ultimately do. Technically, though, the work I do from 9 to 5 is in the public health space. And so it probably would be, generally acceptable if I just said I'm an informaticist and just left it at that, and, not even really qualify it, because I do kind of have my foot in, a couple different areas. And it's interesting because I'm in the process now of interviewing for postdocs. And so whereas I used to teach, in addition to all this other stuff I got going on, I've stopped teaching to make room to start working on my postdoc. And I actually am planning to start next month. So I'll definitely still be in the health informatics space. And matter of fact, I think that's going to be my title, health informatics postdoc or something like that. So I'm not really sure. So it really kind of depends. I want to say one more thing about this, because I think there's a lot to be said about putting something in the universe too. Now, I'm not actually projecting. I actually do that work. But I would say if you are a data analyst right now and you really want to be a data scientist, and you're doing data cleaning and data munging and data analysis, and Tableau and database, I would call myself a data engineer. That's just me. I'm just saying, even if you don't have the title yet. So there's something to be said about putting a title out there, which is kind of different from what you asked me, but I'm just throwing this out here, right? Decide what it is you want to do, get the skill set that match that, and put it in the universe. I'm a real big advocate for verbalizing where it is you want to go and what you want to do. And so even though I never put in the universe I wanted to be a chemical informaticist, it just kind of worked out that way. And I like to think that, I'm a very spiritual person. I like to think that I'm in this space for a reason. It was not my plan. I originally wanted to stay either in healthcare or in HIV. But I knew that for me, what was most important was the work environment. I didn't care well, not that I didn't care, but I felt like whatever I did, as long as my work environment was good, it was going to be okay. And I always loved chemistry, right? That's why I got a degree. I taught STEM to special needs children in high school chemistry. And so I've always been, a chemist at heart. So it was just ironic that I ended up back in this space. So that's a real long, convoluted answer. Actually, somebody's asking a question between data engineers and data analysts. Absolutely. For me, data engineers are real good about pulling data from out of the cloud and getting it in a framework and a format that can be analyzed by data scientists. Data analysts are actually more concerned, at least from my positions, with more real-time, you know, how many patients came into the ER that got diagnosed with HIV? So that's the area that I work in. How many of those HIV patients actually got COVID, right? So data analysts for me in a healthcare space was about real time, what's the status of whatever situation I'm in today? And those positions can be different too. Actually, one of my other data scientist positions should have been data visualization expert, because all I did was code in Tableau, right? So it really kind of depends. A lot of these titles are interchangeable, but data analyst and data engineer is not one that's interchangeable. To me, they are very different skill sets. And like I said, I'm data engineer, no. All righty, okay, so it looks like that ran. It took 6 seconds, that's kind of slow. Okay, so I import RDKit as Kim. These are packages that are already described in RDKit. If you Google it, you can get more information. What's important here is, remember I talked about those descriptors. So what I'm saying here is that I want to be able to chemically represent the structure of this compound in a way that will allow me to create fingerprints from which I'm going to calculate my Tanimodal coefficient. Okay, so then I also import Cal molecular formula, which is basically a package for calculating the molecular formula. So now I have smiles. You guys may remember that CCO was the isomeric smile for ethanol. So I want to change that into what I'm calling mole 1. So I have 2 substances. The first one is ethanol. So I'm going to convert that smiles into ethanol, and you can see it does it here. And then I have another conversion. So remember, I want to compare a known potential mutagenic impurity with ethanol. So here, what I'm doing, I have the smiles for, this should be dimethylamine. Yikes. Okay, got to get it right, because diethylamine is very different from dimethylamine. So dimethyl nitrosamine this is the smiles for dimethyl nitrosamine. I'm going to call that mole 2. And then I end up with this particular structure. Okay, so you can see that it has the oxygen compounds are highlighted in red, it has the nitrogen highlighted in blue, and then the carbon bonds are in black. So now I need to import a couple more packages in order to ultimately be able to calculate my my Tanimodal coefficient. This again is all described in RDKit. If you go to the website, you can pick it up. And I also import NumPy as NP, so that I can use some of the feature and packages from NumPy. That runs okay. So now, just to check it, I'm going to take the smiles and convert it back to, I'm going to take the mole, the description mole 1, and I'm going to convert that back into smiles just to make sure it works. I just kind of double check things that I do. And then just for fun, I wanted to see what the molecular weight was. Remember, I imported the package to calculate the molecular weight, the very top line, and I get 46.069. And I'm able to verify that with the information I got from PubChem. So now, again, I just kind of playing around with it. I want to see what the molecular formula is. I'm just trying out all the different features of RDKit. So this is actually how I went through this process, right? So I got this assignment. I'm new to chemical informatics. I'd never used RDKit before. This is probably like the 10th time I've used it where I'm showing you now, because I literally just started about 2 months ago, but I wanted to share it because one of the best ways to learn something is to teach. So now I want to see, let's see what the molecular formula looks like. So C2H6O, and we know that that's the formula. Okay, so now I'm creating what I'm calling a smiles list. Well, I said smiles list, actually. Smiles list, which I have my smiles, and I'm going to create a list from that. Okay, so this is a basic for loop in Python, and what I'm going to output are the 2 images that I'm looking to compare, ethanol and dimethyl nitrosamine. So this is the code for that. And again, this will all be available in January, but if you want quicker access, just go to rdkit.com and then substitute whatever substances you want to look at. So now I have an image, and these are the 2 images. And so if these match back to what we had before. So for me, I kind of do a checks and balances as I'm going, just to make sure things are going correctly, because it's much better to have to go back 1 or 2 steps in code than to have to go back all the way to the top. So I kind of do these checks and balances as I go along. It's a little AR, but you know, it's me and it works. So here we go. All right, so now I'm just out of curiosity again, I want to see how the package works. I want to look for a carbonyl group. Is there a carbonyl group here? Let's see. And yes, there is a carbonyl group. So it's evaluating this first compound. Actually, I guess we got these backwards. So it says true and false. I'm sorry, not a carbonyl, a C bonded to an oxygen. Correct that. And yes, in the first compound, there's a carbon. It's bonded to the oxygen. The two atoms are right next to each other. And then the second one, that's actually a nitrogen and an oxygen there. Okay, let me get this chemistry straight. So now I want to look for a pattern. The pattern I'm looking for is there an aromatic ring? That's what the R stands for. So now what's key with this part is that I'm using something called SMARTS, which is supposed to be a smarter version of SMILE. So it enables you to look at aromatic compounds and to be able to retain more stereochemistry. So I'm not describing any SMARTS, I'm not describing SMARTS the way I've described SMILES, but I'm just describing or just telling you that that's what I'm using here in order to determine if there's an aromatic ring. And so for those of us who know organic chemistry, and I think that's probably everybody here, there's no aromatic ring. That's what the R stands for. Again, I write a for loop to parse the mole list that I created, and I'm looking for a pattern match to an aromatic ring, and I should get false, and I do. Okay, so here's the really interesting and cool part. So now I want to create some fingerprints, and then ultimately want to look at the tantamodal similarity tantamodal coefficient. Now you might remember in Python, indexing starts at 0 and not 1. So I have my mole list, and the first substance on my mole list is actually the ethanol. So we're just double checking to make sure that that's correct. I'm going to call that ETOH, and that's what comes back. Similarly, for the second item on the mole list, again with indexing starting at 0, this would be item number 1, and I'm just giving it any name: dimethyl nitrosamine, DIMEN, and then I get that compound back. Okay, so here's where you start getting into using an algorithm to evaluate the structure and then ultimately end up with what's called fingerprints. Now, I'm going to demonstrate it first, and then I'm going to come back to my presentation and explain it a little bit more. Oh gosh, I got to get this time together. Okay, so this is the code which is used to create the fingerprints. And remember, the fingerprints take the 0 and 1 pattern, and it creates a structural representation of the molecules that we're looking at here. So, excuse me, it assigns these specialized numbers. And again, the more details about it are in the paperwork or documentation. So ethanol, the fingerprints that it assigns to ethanol are 80, 222, 294, 807, 1057, and 1410. Now, Python has a way of assigning fingerprints, and R has a way of assigning fingerprints. They're not the same, okay? But again, there's more details about how you get to that information if you look in the documentation. All I'm really interested in are what the results are. And then ultimately, if I can compare the results to the second structure that I'm going to look at tonight. So these are the 4 numerical representations of fingerprints which were created from the substance ethanol. So you kind of got to keep that in the back of your mind. What does that look like? So I want to take that numerical representation, which is based on a specialized algorithm, and I want to draw a structure from that. So the first bit here is 80. To turn it into a structure, I use a specialized code in the RDKit called draw Morgan bit. So it's going to take the bit, convert it to a structure, and this is what I get. Okay. So this blue represents one of the main atoms, and the 2 asterisks represents the fact that there are things connected to those other 2 atoms. So let's take a look at all of the Morgan bits and see what they look like. And these are all the fingerprints which have been converted into substructures of ethanol. And if you look at it, it kind of makes sense that this is what they look like, right? I mean, you can see how, starting with the structure of ethanol, how it could potentially come up with these different substructures, which are based on a specialized algorithm, which uses bits, zeros and ones, puts them in different sequences, and then outputs a specific structure. So this is really, really pretty complicated, but at the same time, it's also really cool that we can do this in the first place. So these are the fingerprint structures for ethanol. So I'm going to repeat the same thing with the dimethylethylamine. Uh-oh, FP2, where's FP2? I didn't define FP2. I'm not define FP2. Oh, okay. All right, so this name is incorrect. So let me correct the name, and then it should run. And there it is. So these are the numerical fingerprints that are associated with dimethylethylamine. Again, a specialized algorithm that breaks the structure into substructures, converts those numbers into the physical substructures that we see here. And this is what I'm calling FP2 diethylamine, the designation. So again, if you look at these substructures, which were created from these fingerprints and based on the original structure, they kind of make sense, right? At least they should make sense. So it's like this structure here, 179, we know that when we see an asterisk, that means that there's another atom there. And in this example, the atom that's here would be an oxygen. Okay. So now we have our information. So again, I just go back and, look at the main structure again. I'm double checking because remember, this is one of the first few times I'm doing this and I'm not sure. So now I want to I have my 2-bit list of numerical information related to the structure of the substance. Now what I want to do is compare them, see what substructures they have in common. Now you can eyeball this, but some of these more complicated structures, you could end up with like 50, 100 different substructures. And those you can't eyeball and figure them out. So this is pretty easy. I mean, you can look at and tell that there's one bit that they have in common. But the way that you can check that, again, using Python, use the set function. We compare the results of the 2 bits, and then we end up with bit 1057. So let's look back at 1057. So this is the structure for the bit that both dimethyl nitrosamine has in common with ethanol. Now, at this point, I'm saying, okay, they only have one thing in common. So the chances of these 2 substances being similar is not very good. But let's go back to our organic chemistry for a second. Ethanol is a functional group alcohol. Dimethyl nitrosamine is a nitrosamine. They have very different chemical properties. So this is an example of where one needs to be a chemist to really understand the results that I get. Do the results that I get make sense based on the acid-base characteristics of the substance I started with? Based on when you're dealing with substances that have like benzene rings, now you're dealing with resonance structures. So all of that information comes into play when you're looking at the results that you're getting at every step. And that's why it's important to have the subject matter expertise in chemistry. Okay, so let's go down to the bottom here. But you're like, what does this have to do with machine learning? I'm gonna show you in a second. Okay, so I have my 2, I know that they only have one in common. So my guess is that these are not very similar, which I kind of knew from the beginning because one is an acid, one is a base. And so, you get different chemistry just based on that, right? So I'm gonna put these all into one combination that I'm calling combo 1. And then I end up with this output, which are all of my numerical representations of my substructures. And now I compute them using what's called a similarity score. So one way to do this is you print the length. Common 2, common. All right, correcting some code here. So when I do just a basic you know, how many do they have in common divided by how many they, you know, have all together, we get a result of 0.0714. That's really, really low. Because remember, the tiny molar coefficient being an indication of similarity has to be greater than 70%. So, but when I use the tiny molar similarity package, which is already in RDK, I get the same number. This is just a check. So now I have this information. Well, now what do I do with it? So this is where I'm actually at in the project. I've just got this all worked out. My next step, and I'm going to go stop sharing screen and show you, go on to exactly where the machine learning part would come in by going back to the presentation. And my apologies that things are moving along a little slower than I thought they were. They would. Okay, so I go back to the presentation, and now we're going to pick up with the machine learning. But before we do that, I'm gonna digress for a second, because I started, when I was advertising that I was having this talk, one of the things I talked about was, I mentioned, what does caffeine and Viagra have in common? Now, do not shoot the messenger. If you go to ChemInR, the website, and again, I have it linked, I have it listed as a link in my references spreadsheet. This is their example. Okay, now let me be clear. I will not be presenting this at work. I'm the only woman on the team. I will not be mentioning this as an example when I have to do this presentation at work. Okay, that probably isn't going to go over well on an all-male team, especially all-male teams with people who are up in age. I'm just saying. So I'll come up with some other examples to use to compare to, you know, as an example of R. But I bring this example up because, again, it's the one that was using ChemInR, and obviously I don't have time to go through it. But using the same type of technologies in terms of fingerprints, and then creating algorithms that make calculations about, you know, atoms that are associated with each other and the bonds that they form, and, you know, whether or not they have a charge, or, you know, all those different type of things. So what does caffeine have in common with R? It's highlighted in red. You have this 6-member ring, you have this double bond, you have a carbonyl group, again, 6-member ring, double bond, carbonyl group. You have a 5-member ring, pyridine, I think is what it's called when it's a 6-member ring with the 2 nitrogens. Don't quote me on that. At any rate, you can see that they're a very similar structure. Caffeine and Viagra have very similar structure. Now, I don't recall off the top of my head what the tiny molar coefficient is. I think it was like about 50%, because as you can see, Viagra has all this other stuff. But think about it. When someone was designing this drug, they thought, okay, what can keep me awake? Maybe I could start adding some different things to that. And here we have something that looks like caffeine right in here in Viagra. So this, again, is just to show that when you're doing machine learning, Chem Informatics, you can either use R, you can use Python. I just thought this was kind of funny, but like I said, I won't be showing this one at work. Okay. So now that I have those fingerprints and I have my tiny molar coefficient, so what's next? So QSAR stands for qualitative structure activity relationship. So what we do with that information is we use it to, the next step would be to do a machine learning method model, because what we ultimately want to do is come up with a way to parse a group of substances and make a determination, is it a potential mutagenic impurity or is it not? Okay, so this is taken from a paper, which again, I've referenced. We did this part already. We have this chemical compound here from our compound database. They created, these are the descriptors, where you see these asterisks here, these are descriptors. These descriptors are then read into, which represent these different types of structures. They're coded into 0s and 1s to make it machine readable. And then they take that and create a tiny molar coefficient. So in this case, they had molecule A, molecule B, and they determined that they are 23% similar. And then from there, you can go on and do your instance-based or model-based learning. Now, I've already kind of looked at all of the different machine learning methods. And the two that I'm focused on, I think would work the best, are either going to be logistic regression. And I'm choosing logistic regression because my output the endpoint is categorical, and it's either going to be yes, it's a mutagenic impurity, or no, it's not. But then you can also use support vector machines. And so with support vector machines, there's a hyperplane that's created. you have all your different compounds, and they're going to fall either above or below the hyperplane. So again, we have that separation or that classification of substances that are either be potential mutagenic impurities or not. Now, some other methods that people use in chem informatics include naive Bayes. I don't know really a whole lot about these, or K nearest neighbor, but I did find that K nearest neighbor was a lot about how they determine the fingerprint out. The algorithm for the fingerprints and descriptors is actually based on the atoms that are next to whatever that primary atom is. So I thought that was really kind of a coincidence. Although again, I'm very new to the field and don't really know all the intricate details as it relates to, you know, all of the mathematics, for example, behind the descriptors and the fingerprints. But I do know that they're related to K nearest neighbor. Now, in what way? I'll find out when I do part 2 of this presentation. So again, the diagram, you have chemical feature extraction, you have chemical fingerprint creation, which I showed you in Python. And then my next step now, I'm going to do the QSAR, QSPR modeling, although I'm going to focus on the structure activity relationship as opposed to the structure. And I guess I just lost it, what the P stands for. I have to think about that a little bit more. I'm doing QSAR though. Okay. So with that, that's the end of the presentation. These are my references. If you want to screenshot this and get a look at it before I'm actually able to make these available, that will be perfectly fine. Give you a second to screenshot. There's some really great articles, but with all of that said, this is a really, really super new area, application for informatics, a new application for chemistry. What I can tell you is that there's a ton of opportunity in this field, and please ignore my howling cat in the background. There's a ton of opportunity for people that who are, you know, you don't want to be at the bench anymore, and you want to move on to something else. Again, it's really new. There's lots to learn, and I'm really enjoying doing it. And I got folks from pharma, folks from all over throwing a lot of money. Okay, so if you're motivated by money and having a little fun, this might be a good one for you if you're a chemist or a biologist even, and you're ready to come out of the lab. And with that, I will end my presentation. Righty, does anyone have any questions? No questions? Let's see if I look in the chat here. Ooh. Okay.
I have a question.
Sure, go ahead, Amanda.
Hi. You said that if you're a chemist or a biologist, that this could be a potential field. What if you don't have that science, but you have the data analytics, you're interested in the Python and the kind of coding and machine learning?
Well, I think one of the things I always talk about is what do you want to specialize in? I kind of got to this by accident. I just wasn't on my radar whatsoever. I would say that if you want to apply it in a STEM field, then you need to become STEM fluent, right? That's really super important. And what I mean by that is I don't mean go out and get like a bunch of degrees. It doesn't necessarily have to be that, although it wouldn't hurt. And having the degrees will open up a lot of opportunity. But you can, like, for example, there are classes in like drug discovery that are actually on Udemy, but you're kind of going to have to get the science background or whatever background, right? So let's say if you want to be a financial data analyst, it would be helpful to know some finance. If you want to be an educational data analyst, it would be helpful to have some education experience. And so it really just depends on where you really want to focus. I think one of the things that I really wanted to emphasize, everything I showed you is applicable to anyone in STEM, right? So if you had a biology degree or any degree, mathematics degree, you can certainly learn this information. It's just that for something as specialized as chemistry, I would advise like some courses at the community college, general chemistry, organic chemistry, if that's the area you want to specialize in. You don't have to get a degree necessarily, but I definitely think it helps.
Thank you. That was very helpful.
You're welcome. Any other questions?
We got some comments saying your session was fascinating and also very informative.
Thank you. Yeah, it's really, really kind of deep, and I hope I didn't gloss over too much stuff. I just really want to kind of show that, especially again for people that are feeling here's the thing about the whole STEM degree, because one question that I do get asked is, why didn't you get a PhD in like chemistry or biology, whatever? And the answer is because of the job market. I never had an interest in getting a PhD, like ever. Okay, that just wasn't it. Well, let me take that back. I did have interest in getting a PhD, but with an MD, right? I never thought for one moment about getting like a PhD in chemistry and biology because, you know, having worked at the NIH, I'd been a fellow there. When you go to career fairs at NIH, the rooms that are standing room only are the ones for postdocs and PhDs, and the market is just really, really incredibly challenging, except for people who have PhDs in like informatics or analytics, you know, anything dealing with software and data. It's a whole different ballgame, which is why I did what I did. I ultimately, well, one thing is I want to teach at the university level. Excuse me. So I need a PhD for that. But the other part was that I wanted to not have any limitations in job opportunity either. So that's why I decided to do the PhD. It is not required. You can get a master's degree, especially in informatics, especially in data science, and you could just cruise right there. In other words, I will have a PhD and will know plenty of people making more money than I am with less education. So it's all about what you're interested in. But I always tell people, if you have a desire and you have a way to get it funded, to go for the highest degree in your area, with the exception of, not even exception, I won't say that, like, because if you want to get like basic science, like, I don't know, pathobiology or something like that, those are all great degrees. There's nothing wrong with that, but the competition is significant. So if you're going to go that route, learn how to program. I tell people that all the time. If you're going to get that basic science degree, learn how to program. And that's what I tell undergraduates, that's what I tell master's students, learn how to program. And if you don't really want to do the programming thing, then learn how to visualize data, right? Because you can drag and drop in Tableau for that, right? Definitely learn how to analyze data for whatever you do. Oh, somebody's working on QSAR modeling. Very imbalanced. Okay, so can you unmute yourself? I don't want to mess your name up, Sam. I'm just going to say Samuel. Can you unmute yourself and say what you mean by unbalanced? Because that to me means a lot.
Right. Can you hear me?
Yes, I can. Thank you for the question.
So, yeah, no problem. I like to talk. I'm going to use some of the ideas when I'm explaining it to undergrads myself.
Mm-hmm.
So in my case, I am trying to predict some biological activity.
Mm-hmm.
And I have some experimental data that I'm going to use to build a model. But as is usually the case, most of the results I have, most of the data is from inactive molecules, and I only have a handful of active ones. So in that case, if you try to build, if you aren't careful and you try to build a model, what usually happens is that it will tell you that everything is inactive, and you'll get 95% accuracy anyway, even though it's not actually meaningful.
Mm-hmm.
So I'm trying to figure out ways to work around that, where I don't have enough active examples to train a model to recognize active examples. So in that case, I'm looking at like maybe 1% to 5% of the molecules are active compared to the inactive ones.
Mm-hmm. You know what? I'm going to tell you, this is a question that's more about what do you do in general when you don't have enough data, right?
Yeah, it is.
Because actually, so there's a story behind this with me. I had originally planned to do for my dissertation project, I was looking at, I had done a lot of work with cancer. I'd worked at the National Cancer Institute. I had worked at MD Anderson. I had worked at, a lot of big organizations with cancer. So that's what I really ultimately wanted to do. But I wanted to be health disparities, right? So I got to the PhD program, and the second one, by the way, because the first one didn't quite work out, transferred after a year. That's a whole other story. But at any rate, I'm going to graduate from Rutgers next year, so it's all good. So anyway, so I'm at this program, and I found this researcher, and I'm like, she's doing some, looking at genomic influences in how people metabolize anti-cancer drugs. Okay. So I had a bit of background in pathology, and originally had wanted to become a pathologist, which is another story too. But anyway, so I was really interested in pathology. And so, I'm looking at all this data, and I'm looking at all of the sources of tissue that I will need to do genomic expression analysis on. And I'm realizing that in a publicly available database, there may be 10 patients who have donated kidney tissue at that point for, for use for research. Now, obviously, I can't build a dissertation on 10 samples and ultimately change to doing HIV. So what I would say to that is, if you don't have enough data, there's one thing you could, I'm not sure how this would apply in Chem Informatics, right? Because I haven't been in the field long enough to see all of the nuances. I can tell you what I have done in other fields, right? When I don't have a big enough sample size, you can impute the data. I don't know if that works in Chemical Informatics. I'm just throwing something out here, right? And create some additional structures that are similar to the ones that you already have. So the way I would impute data for, say, age groups, say I've only got a sample of 10 people, ranging in age from 10 to 30. So you can use as a program in R that you can use to impute data to create an additional, data points to add to that set. And then you just have to mention that you imputed the data. Now, I don't know that that would work for Chemical Informatics. I suspect that what you probably have to do is either think about reaching out to other investigators that do research too and see if you can pool your resources and go from there. Or you might have to try a different method. So again, using my own research as an example, I originally wanted to look at neural networks. I'm like, okay, that was the biggest thing. That's sexy. I'm gonna do neural networks. I did not have enough data to do I don't have enough data to do neural networks. So I bought myself back on down to logistic regression and we're gonna roll that out. Okay.
Right.
So that's just an example. Again, I don't know that it would be applicable, but I do know that data size, I'm not sure what you could do in data. That's actually a good question. I don't know if you can impute chemical structure data. That's a good question. I don't know.
Yeah, some people do, but in my case, it's not really an option because the descriptors I'm using are very specific and they only take discrete values. So there's nothing really in between. So you could create in between numbers and descriptors, but they wouldn't correspond to an actual molecule.
Yeah.
So that's what I'm trying to figure out over the next couple of weeks.
Yeah, I think I would try to partner with other people that are doing something similar to get some data that way. Are you a member of ACS?
Yes, I am.
Okay, did you reach out to anybody there? Because see, my thing is the answer to the question. It's just, what are you going to do to dig around to find it, right? I just don't believe it. No, I don't take
the only problem is that no one else is working on the molecules that we have. These are molecules that we created in-house specifically for this purpose. The only other way to get data is for us to generate it ourselves. Which takes a while.
Yeah, but you might have to. Yeah, I don't know. That's a tough situation. I'm not really sure.
It is. Yeah, but thanks for your time.
No problem, and thanks for sharing.